So welcome back. We're happy today to have Dennis Gaitsgory giving the second of his two Bott lectures on function-theoretic consequences of geometric Langlands.
Thank you very much again for the invitation. All right, so this is the second talk, and unlike the first one, which I had given a bunch of times, this is the first time I'm giving this one, so I can say some very stupid things. All right. So what I'm going to do, I'm going to give some applications, rather one application of analytic flavor of what we did yesterday. And of course, I'll recall whatever information is needed from yesterday's talk for this one. All right, so to recap, we have a curve X over a finite field, and we have a group G also over a finite field, and we consider bund G the moduli stack of principal G bundles of the curve. And today we're interested really kind of the set of isomorphism classes of its FQ points, and we want to study functions on this with finite support, and for now with C coefficients. And here I'll assume that G is semi-simple. I don't want connected center. Now, all right. So, and we want to study, well, as is the most classical thing to do in the theory of automorphic functions, we want to study this as a module over the Hecker algebra. So what is the Hecker algebra? So fix a place close point in X, and you can consider, so Kx is the field of local field at X, and OX is the local ring at X. So we consider this double quotient, and we consider the algebra of compactly supported functions on it, let's say also with C coefficients. And so there's a standard procedure, which I won't recall, that this algebra acts on this space for every X. And let me call it, what do I call it? H. And I'll write C to indicate coefficients. So it acts here, and for different points, these actions commute.
And is it acting on the space bund G or the space of function?
The double quotient acts as a groupoid on the space, and the algebra functions on that acts on the algebra functions of space. All right. So, so we're interested in studying the joint spectrum. And so let me define what I mean by cuspidal functions. Here's a very concise definitions. And it's due to, I think it's due to Vincent Lafforgue, and maybe it's a very elementary observation, but it's extremely useful. So cusp any coefficients is a subspace. Well, let me write it. It's equals the space of those functions that are Hecke finite. So what I mean is that just take those vectors here, which are locally finite with respect to this algebra, which under the action of the algebra span a finite dimensional vector space. And so we want to study generalized eigenvalues of this product of algebras on the space. Well, I should also say you can using some unitarity trick, you can see that this actually is diagonalizable. So generalized eigenvectors are eigenvectors, but that's not the point here. So want to study systems of eigenvalues of this product of this Hecke algebras on the space of the cusp functions. And I'll now want to say something how we want the spectrum to look like, and that something is known as the Ramanujan conjecture. All right, before I want to describe how these algebras look like explicitly, so here's how they look like. So so they're all isomorphic, abstracted to each other, and see how I wrote it. So it's the algebra of regular functions on the Langlands dual group that are ad invariant. And so this is the same thing as functions on the GIT quotient by the group of itself. So this double backslash means GIT quotient, and single slash will mean stacked quotient, and this distinction will become important. So, i.e., so maximal ideals of this, so the potential eigenvalues, so of any such hx are, you can think of them as semi-simple conjugacy classes in G-check. Let me write of C. All right. Sorry, I'm looking at my notes. I have this phobia of forgetting something. All right. So suppose you found such an eigenvalue of the action of these guys on the space of cos forms. So what is it? It's a system of like lambda x running through the closed points of x. And each of these guys, as we just said, it's a semi-simple conjugacy class. Okay, so now I'll state the naive Ramanujan conjecture, which is false. So naive Ramanujan says that if you have the system of eigenvalues on the space, then all of these conjugacy classes are compact. So it's a theorem due to Laurent Lafforgue for GLN, but it's known to be false for other groups. And what I'll state next is a correction to it, which is a theorem that I'll talk about now. Any questions so far?
Why do you feel like that? It looks like you're just saying each lambda x is compact, so why do you consider the set of, why are you writing them in the set of all of them in x point 6? What is the purpose of? Yeah,
whatever. You know, it's what just logical. It's the same.
Well, what is the reason for putting them?
Because tradition, Hecke eigenvalues, yes, and the datum of such things is very close to datum of local system for length.
There's no relation.
No. But you're right. You didn't have to. All right. So, yeah.
So is it any sense continuous? Not like SX vary.
So that's exactly Aaron's. So you'll see what in 10 minutes, you'll see what all these guys are, what they look like. They're not continuous, they are encoded by Galois representation. That much is true. So it's not a disparate collection, it's really kind of one Galois representation that. All right. Where am I? So here is the correction. And the correction looks as follows. So fix is kind of a simultaneous eigenvalue. So maybe here it becomes important. So then because otherwise the statement I would say would be weaker than what it is. So it takes a simultaneous eigenvalue, then so for each value, there exists a correction, and that correction is the following thing. It's a homomorphism, let me call it phi sub e from a copy of SL2 to G check. It's an algebraic homomorphism such that the following holds. So let's denote by HE the centralizer of the image of phi. And it's also a reductor group potentially disconnected. So then what we're saying is the following. Then each of these lambda x's will have the following shape. So I'm looking at my notes. I just so it's a conjugacy class that looks as follows. So it's a conjugacy class of H times the image by means of this phi of a toric element in SO2, which is this, and H is compact. Class in H of C. So this is the corrected Ramanujan. So we have to correct the initial compactness in H by the following thing. You shift by this element that comes from SL2 times something compact in the centralizer. And so this is correct Ramanujan. And this is the theorem that I'll try to explain today. So this is joint work with Vincent, Lafforgue, and Sam Raskin.
Sorry, can you clarify the statement? Lambda x is a subset of, it's a subset of the group. And
so I'm saying that lambda x as a conjugacy class, it has the following shape. So I wrote it badly. It looks like this. First of all, it makes sense to take the product because these two guys commute. I take this element in the group times an element in the centralizer.
so what is little h? It's a conjugacy class.
Conjugacy class in HE. And that guy is compact. All right?
It's on X.
For all x.
Sorry?
For all x.
Yes, so little h depends on X, but big H doesn't.
Where is big? Yeah. So that's exactly why I wanted to consider them simultaneously. For each simultaneous eigenvalue, there exists one homomorphism like this that is fixed, such that for all h's, so for all x's, that will hold. Yeah. So I'm also a little bit under the weather. I can be saying complete nonsense. So please correct me. So the corrected Ramanujan may require further correction. So it's what you're asked. Like if you take simultaneous eigenvalue for all these h's, yeah, for that there exists a phi e. Make sense? All right. Qx. Q. It's very important. It's the residue cardinality of residue field at the point x. Thank you very much. All right.
The PE, is that different from P? And also is that also?
Thank you. All right. So now let's prove it. All right. So now I'll recap what happened yesterday. So let me just first say that, diverges slightly from my notes, this is not about complex numbers. So everything is defined over Q, and essentially what we're saying is this eigenvalues are Weil numbers under. So that's what it's about. Just I wanted to say this. All right, so let's head towards the proof. So what did we say yesterday? Oh, I see. I don't have to do it manually, but I like to do it manually. So, what we said is the following: if you consider this finitely supported functions, but with QL coefficients, so this space is isomorphic to the following. So we take the space of global sections on some moduli stack that I defined yesterday. The precise definition will not be so important for this lecture. So it's arithmetic local systems, and on it I take the dualizing sheaf omega. So that's what we proved. And note that so both are Analytic vector spaces. So now I have to say how this behaves with respect to the Hecke operators, because that's our interest today. All right, so let me introduce this notation. I'll call A excursion. That's the excursion algebra that appears in the work of Vincent Lafforgue. So that's the following thing. It's the algebra of global functions on this guy. Not sections of omega, but sections of the structure sheaf. So first of all, let me say it right away, is that if you look at this guy, it's totally not clear a priori that it lives in cohomologically degree 0. So this stack, first of all, it's really derived algebraic stack. And so this omega lives in positive and negative cohomological degrees. If you take global sections a priori, it may be spread in both directions. But due to this isomorphism, it happens to live cohomological degree 0. So now let's look at this guy. So the stack of local systems is a quotient of a derived defined scheme by reductive group. So therefore, when you take global sections, a priori, it will live in non-positive cohomological degrees. So what we call connective. Totally not clear a priori that it lives in cohomological degree 0, but it does. So let me just say a little lemma. It's actually classical algebra. All right. And if you take any sheaf, if you take its sections, this algebra of global functions will act on it. So this guy acts on this. All right.
About the statement, I'm still a little confused.
Yes.
It looks like you're saying that X is this compact conjugacy class times
Yes.
some element.
Correct.
But then does it have to be compact if you just take something compact and multiply it?
But the element is not compact.
Wait, not just one element?
Yeah, it's just one particular element.
What point does it have to be compact?
What do you mean, which point?
Oh, I don't know. I thought one element is like one point in the group.
So it's the point in the group SL2, and which point is that? Is the toric point with these entries.
Yeah.
And it's clearly not compact. The eigenvalues are not in the unit circle. All right. So we have this local system arithmetic, G check, and it projects tautologically to the spectrum of this algebra, which I'll denote Lox's G check arithmetic course. This is the course moduli space. Again, by definition, this is the spectrum of the excursion algebra. And so I forget who asked about how this eigenvalues cohere. So I'll say that in a minute. So general GIT tells us what the closed points of this thing are. So the closed points of this are semi-simple, so isomorphism classes of semi-simple Weil local systems. So this is moduli stack. So points here are just local systems as they are. They don't have to be semi-simple. And this map is the semi-simplification. So it contracts points with the same simplification to one thing. And so these guys are what's called the kind of classical Langlands parameters. You'll see. That's what it's all about. Yeah, that's where we're headed there. All right. So now let me say what this picture has to do with the action of Hecke operators. Let's pick a point on the curve. So in this case, you can consider local systems on your point. And if you think of what it is, this is the stack quotient, G check mod G check. Restriction. You can restrict the local system from the curve to your point. And also here, you can consider the corresponding moduli space, which is exactly our coarse quotient. And so you have this commutative diagram. So these are affine schemes, these are stacks. But you can pull back functions. So here you have the excursion algebra. And here you have the algebra of invariant functions. So now the way this isomorphism works makes the following, kind of implies the following compatibility statement. So start with an element here, and you can do two things. One thing is this Hecke action, apply, where was it? Oh, it's gone. This Satake isomorphism with hx and act on the space of automorphic functions, or map it here. So this excursion algebra, as I said, acts on sections of omega, which is isomorphic to the space of these automorphic functions. These two actions coincide. So I've given the expression on the geometric side to the action of the Hecke algebras. And again, to just recap so they come from this diagram, have to do with the restriction of the point. Aaron, you look unhappy with this.
I'm sorry, I'm still confused about how you can take a compact set and multiply by a single point and get something not compact. How can a point not?
No, so it's not the question of the set being compact. There's a notion of an element of a group being compact. And that means that it's conjugate to the maximal compact subgroup, to a maximal compact subgroup. So I'm saying this element in the group is compact. It's an element, it's a compact conjugacy class, if you wish. Eigenvalues are on the unit circle. So that's what it means. So I'm saying that the eigenvalues here are not in the unit circle, but up to this.
Oh, so that's what lambda.
Yes. Okay. Yeah. So happy now?
Yeah.
Okay, how about this?
Gotcha.
You were talking about some compatibilities.
Yeah.
On the local system side, what's the actual structure? On the other side, it's an action.
On the automorphic side, the Hecke action, right. And I'm describing it on the spectral side.
But it's also an action.
It's also an action. Yes. So first of all, I have an action of this on this. Agreed? And I have a homomorphism of algebras from here to here. And so that's what the action is. Apply homomorphism and then act. Is it okay? Yeah.
That seems very abstract. Suppose I don't know anything about that. I still know about local systems, right?
Yeah. So that's the information that will be, that's the only information that we'll need. So again, I'm saying that. So all you need to know is that global functions act on sections of any sheaf, And I'm saying that how this particular algebra maps to this, the algebra of global functions. And it maps by pullback by this map. And what is this map? You have a local system in the curve and you restrict it to a point. So that's all I'm saying. Kind of that. So that covers all the information that we'll need from the story. Yeah.
So it seems like this excursion algebra is bigger than the entire Hecke algebra. Can you describe this action on the other side?
It's a very good point. So before I forget, so for any point x, you have this homomorphism. And you can take the tensor product of these homomorphisms over all x's. And for GLN, it'll be surjective. And for other groups, it won't be surjective. But what is true is that even for one point, this is finite as a module over this. So that much is true, kind of easy to see. So let me just say it, that it's a finite map. This is a finite map of a final algebraic. It's kind of very important for the future.
So there's a lot of redundancies across points.
Not call it redundancies or lack of information. Like when you act by Hecke functors, you don't capture everything. So like the whole point of Vincent's work was that if you want to recapture the Langlands parameter, so it's the spectrum of these guys that is semi-simple local systems. So you need to action all of this. So the actual Hecke algebra we've had for 100 years, it's the action of this guy that was a new phenomenon.
What is the statement? Is there a statement on that, or is that just commute?
No, so that's kind of, this is the tautology. I'm saying it's map of stacks, gives rise to map of coarse modular spaces. The statement is that the resulting action of this via this homomorphism on this equals the Hecke action of this on this.
So that doesn't use anything about that square. That's not.
About?
Okay, thanks.
No, it's this square is just, you have this map of stacks, just take the corresponding map of global sections. All right. I really appreciate the questions, by the way. So the more
The point is that
this one.
it doesn't act on the left map. It doesn't act.
So it maps to global functions, and therefore it acts on sections of any sheaf. On sections of any sheaf, in particular omega, and that is what we're interested in. And let me just put it on the blackboard. So let me take into account this finiteness statement. So here is, like, let me reformulate Ramanujan. So take an eigenvector, well, eigenvalue of this A excursion acting on global sections of omega. So you have this eigenvalue of the excursion algebra, therefore you get eigenvalues of this algebra. Ramanujan tells you something about it. So like Ramanujan tells us what the corresponding eigenvalues are. And know that this eigenvalue is the same as a local system. So eigenvalue, so note that such an eigenvalue, it's a maximal ideal in this algebra, so closed point. is isomorphism class of semi-simple local systems. So, for example, the naive Ramanujan is exactly the statement, so let me semi-simple class local system, we call it sigma, that is equivalent to sigma being pure of weight 0. So there is a notion for locals, for Weil local systems to have weights. And if you just recall what it means, just Ramanujan says exactly that, naive Ramanujan. And what we are seeing that it's not quite true. So this maximal ideals that appear will not necessarily be pure of weight 0, but there is a connection. And so what I'm going to do now, I'm going to give an algebra geometric statement of what's actually going on and then prove it. I want to keep this because it's completely parallel.
Is that
it's omega. So I'm writing, I don't know what I'm writing.
Why is that an eigenvalue? Why is it an isomorphism?
So we said that like close points of this by GIT are exactly semi-simple locals, isomorphism classes of semi-simple local systems. Eigenvalue of an action of commutative algebra is a point of its spectrum. All right. So here's the actual theorem that we'll be proving. It's the following one. So let sigma be an eigenvalue. Of the action of the excursion algebra on global sections of omega. And I want to say something about sigma. So then the following thing happens. Well, there exists a homomorphism phi sub e from SL2 to G check. Same notations. So HE is the centralizer. And a homomorphism, I'll call it sigma corrected. So call it the Weil group. So our sigmas are really conjugates a class of homomorphisms from the Weil group to G check, which is irreducible. So irreducible means the following, that the Zariski closure in the image is reductive, and the centralizer of the image is finite. In other words, is elliptic. So Zariski closure of image is reductive. This condition is semi-simplicity plus finite centralizer. Such that, so how are these two guys related to my original sigma? Such that sigma is the following thing. So I can take my Weil group and I'll send it to Weil times SL2, and I'll specify what this homomorphism is, and then I'll send it to G check by means of this sigma corrected times phi sub e. And now what is this homomorphism? I'm mapping to the product. It has two components. One is identity, And the other is the following guy. So whatever the Weil group is, it maps to Z. It's the Weil group of the point. Let's call this map degree. So this map, let me call it Q half, Q minus half, 0, 0 to the degree. So the second component is trivial on the geometric fundamental group, and it factors through Z, and it sends the generator to this element in SL2. All right. And so I claim that this version of the, so note that I kind of got rid of Weil numbers here. It's a question about something being irreducible, but I claim that this theorem implies this. So let's see what the mechanism is. And the mechanism is deep. It's actually the full force of Laurent-Lafforgue's theorem. So the point is that everything that's irreducible is automatically pure of weight 0. So theorem implies Ramanujan because any irreducible local system is pure of weight 0. And pure of weight 0 exactly means this compactness assertion that I was alluding to.
What is the content of the theorem? I don't know. It sounds like you said there's maps.
So I have an eigenvalue, right? So here is a naive assertion. So this local system is itself irreducible. That would be naive Ramanujan, but that's false. So here is what's true. There exists a homomorphism from SL2 to G check with the following and a homomorphism, I call it sigma corrected to the centralizer, and that guy is irreducible. And how is this pair related to the original one? But this correction. So like the original guy, sorry, this is sigma. The original sigma factors like this. So it's so I can think of it, so it goes to the centralizer, but I can embed the centralizer into G check, and as such, it will commute with SL2. Yeah. I can see, so yeah, now I can see who's asking the question, yes. Say one more time. So, well, there is closure. You can take in either HE or G check. It's the same thing. One is a subgroup of the other. So semi-simplicity means that the risk closure is reductive. That doesn't change. But now I'm looking at the centralizer of this image inside H. And I want that to be finite. Inside H. Yes. This is what you meant, right? Yeah, okay. And its irreducibility inside H guarantees that I'm pure of weight 0 inside H. And then I'm not pure. So this gives the correction how much not pure I am. All right. So
Laurel, so there's some way to reduce to like geometry.
say this again.
You said by Laurel the fact that it's irreducible.
Yeah, it's so what does it mean to be pure of weight 0? It means that for every representation it's pure of weight 0. Like suppose it was not, it would have a weight filter. So Laurent-Lafforgue tells you that every Weil local system is mixed, so it will weight filtration. So, and this weight filtration is functorial, so you have a parabolic. Not good. All right. Okay, so this is the theorem that we want to prove. Let's prove it. So we are looking at global sections of log-cis G-check arithmetic of this omega. But let's remember where it came from. So here we have to recall a little bit what happened yesterday. So this was the trace of the Frobenius on something we called intco nilp on another geometric object, which was geometric. So it was over the algebraic closure over F Q bar. So now I have to decipher a little bit what these symbols mean. So suppose you have Y, it's an object of algebraic geometry which is quasi-smooth, i.e. derived locally complete intersection. And so what does it mean? It means that if you consider, so it's going to be scheme or stack, like in this case, log-cis restricted. So it means that if you consider its derived tangent spaces, cotangent spaces, well, for a scheme, they would live in cohomological, so in general, for a scheme, they would live in cohomological degrees from 0 to negative infinity. Smooth means that they live in cohomological degree 0. That's smoothness. And quasi-smoothness means that they live in cohomological degrees 0 and negative 1. And negative 1 is the measure of how far your quasi-smooth scheme or stack is being from smooth. And you can form something I call sing of Y. Well, naively, you will write it like undergraduate differential geometry course, like it's a union over all points of like this vector space is H minus 1. It's like when you define what's a tangent bundle. It's the union of points of the manifold of tangent spaces. But of course, it's not a set, it's a manifold. Like here, I wrote it naively, but in fact, it's an algebraic variety. And here there exists a theory that says that to every coherent sheaves on Y, you can attach its singular support, which is a subset of this thing. And it measures how far your coherent complex is being from perfect. If your object was perfect, this singular support would be the 0 section. And vice versa, if you fix kind of parallel to the story of singular support that I recalled yesterday. So vice versa, if n is a subset of the sing of Y, you can attach to it a subcategory co sub n of Y. It consists of all those objects whose singular support is contained in n. And then you take the int completion and you obtain int co n sub Y. This is a full subcategory inside int completion of co, which is what we call int co. So no, sing Y is, so it's not a scheme that maps to Y. It's a totality of like H minus 1. It's kind of generalized vector bundle over Y. All right, so who is Y for us? Y is this log-cis restricted. And so you can identify sing of Y explicitly. So let me write it like this. So, okay. Sing of log-cis G-check restricted in this case is the following. So you have a point on the base, which is a local system. And the datum, this element of H minus 1, is an element, if you just play with it, you will see that's an element of sigma of H0, the 0th cohomology of the cochains on your curve of the local system obtained by twisting the coadjoint representation by sigma. So you had the local, let me just say it again, how many parentheses? So you had the local system for G-check, you can associate the local system vector spaces with the coadjoint representation. You take its cochains and you take H0. So this is Sing, and it has the nilpotent locus that corresponds to the condition that sigma be nilpotent. So all right, so that's the meaning of this int-co nilp. But so why am I saying it in this detail? It's because what we're going to see is that so this category has a filtration, namely by closures of nilpotent orbits. So for each E, it's a nilpotent conjugacy class in G check. You can attach to the closure of the corresponding nilpotent orbit inside. And you can consider the corresponding subcategory. So it will be int-co, call it OE bar of this Loxis restricted. So it will be a full subcategory inside int-co nilp. And everything is canonical, it's stable under the action of the Frobenius, and you can take the trace of the Frobenius on that. And what you obtain that on our space, which is the space of automorphic functions, all of a sudden we obtain the filtration indexed by nilpotent orbits in the dual algebra. So this is really kind of a novel phenomenon. So it's not visible from the automorphic side. So we obtain a filtration on the space. So we take trace of the Frobenius on all of this. Indexed by this ease, by nilpotent orbits. In the dual algebra. Of course, these e's will be the same as these e's in the theorem eventually. All right. Okay, so now I'll state the key theorem from which everything will follow. So here is the key geometric theorem. So we have a filtration of this vector space, and let's consider the associated graded. So let's consider the associated graded corresponding to a given nilpotent orbit. So, and the claim is it's the following. So again, here we take Loxis arithmetic for G check, and we take sections of omega. But then we take associated graded with respect to this filtration. So here's the claim that it's sections on Loxis HE. So that's HE that appeared there. Arithmetic, but now already of O, of the structure sheaf. So here I'm using the fact that conjugacy classes of homomorphisms from SO2 are in bijection with just nilpotent conjugacy classes by Jacobs and Morozov. So every nilpotent element can be extended to the homomorphisms of SO2. So I'll add something to this statement in a moment, but again, just let's stare at it. So I'm expressing these sections of omega in terms of now sections of O for a smaller group, which is exactly the centralizer. So, but now let me just make a statement. So, as we said, this is acted on by the excursion algebra, so which is sections of the structure sheaf. Well, and that is acted on by itself. tautologically. So I want to say something about the compatibility of these actions. So there is a homomorphism in one direction that has to do with the just map of stacks in the opposite direction. So because HE maps to G check, of course you have a map from loxis HE arithmetic to loxis G check arithmetic. However, this is not the diagram that commutes. So if you want to have the compatibility of actions, you take not this map of stacks, but you shift it exactly by that guy. So I even wrote here a formula. So this formula makes sense not just for semi-simple local systems, it makes sense for all local systems, it makes sense at the level of stacks. And it defines a particular map from this stack to this stack. So you, on the Frobenius, you shift yourself by this toric element. And so the theorem is that this diagram commutes. All right. So with this in hand, we'll be able to finish the proof of Ramanujan.
Sigma correction, you write to for G. And remember, in other multi-formula, you have this kind of epsilon.
You'll
plus minus one that have conjunction. It doesn't appear.
You caught me. In fact, it's not O, it's a line bundle whose square is O, but it may be non-trivial. And what we're going to see is that if it's non-trivial, this will be 0. So there are two cases, either it's trivial or non-trivial. If it's trivial, it's O. If it's non-trivial, there's nothing to talk about because the whole thing is 0. But you're absolutely right.
This is detected by the
Yes, yes, and like this, if it's 0, like trivial, non-trivial, is exactly the sign, the character that's in Arthur's formula. Right. Yes. So what happens, like if your nilpotent is even, the line bond is always trivial. It only happens for odd nilpotents. All right. So let's try to prove Ramanujan. So I take an eigenvector. Loxis G check arithmetic. And let me find the smallest term of the filtration to which it belongs. So therefore, it projects, let me call it F bar E. It's a non-zero element inside the associated graded. So, and I think of it as and it's acted on by the excursion algebra, but already for this HE. It acts on itself. And let's think, what is it that I want to show? So what if you look at this theorem. So what I want to show that, well, that map is this guy may not, so this map is finite. It's not necessarily closed embedding. This may not be necessarily an eigenvector, but I can split it in eigenvectors. I can see which eigenvectors appear. And what is it that I want to show? I want to show that the eigenvalues that appear are actually irreducible local systems. So this is what I want to show. So we've reduced to the following assertion. So up to replacing HE by G, check, what we want to show that the eigenvalues of gamma Loxias G check arithmetic acting on itself correspond to irreducible local systems. Okay, but now it's a moment to wake up. Let's see what we're talking about. We have a commutative algebra, and we're looking at how it acts on itself, but we're looking for eigenvectors and eigenvalues. What does this mean? It means that we're looking at elements in our commutative algebra that are torsion, that supported points. Well, when can it happen? So, like if the algebra is full dimensional and it's reduced, it cannot happen. And so here is like the geometric assertion here. So I already mentioned that this excursion algebra sits in cohomological degree 0, but in fact, there's a lemma that this excursion algebra, so this is the excursion algebra, is reduced. So these eigenvalues, what they correspond to point connected components of its spectrum. So this Loxias arithmetic course has a bunch of points and full dimensional components. And what the statement says is that the eigenvalues only appear here. And then it's an easy observation that a point connected component is necessarily a reducible local system. If your local system is semi-simple local system is reducible, then you will be able to move it in a family in the coarse moduli space. So another lemma, if you wish, this is lemma 1. The lemma 2 is that isolated points in this coarse moduli space correspond to irreducible local systems. So, and if you wish, this terminates the proof. And making back to your question, so we were studying the singularities, and that omega causes trouble. Like if it was not omega, if it was O, then we would say, yes, all the eigenvalues are indeed irreducible local systems, but it's omega, but there is a filtration. And so on sections of omega, there's a filtration, and the subquotients look exactly like sections of O, but for other groups. And so these other groups come exactly with this correction. And so we catch something irreducible for them up to this Asiltov correction. So that's the mechanism. I wanted to say something else. I wanted to relate it to Arthur conjectures and to discrete series, but I'm out of time.